Let's take a look at our Lesson 2 notes. Lesson 2 here is on sets of real numbers. So that just means we're going to talk about the different types of real numbers there are out there. We're going to classify some numbers and say what type of numbers they are. And so let's go. We're going to make a chart here in just a minute, and it's going to help us classify those things and make sense of that. But let's go over some vocabulary terms first so we kind of know what we're talking about before we get down to that chart down there. So the first vocabulary term is the set of rational numbers together with the set of irrational numbers. So both the rational and irrational combined, those are called real numbers. And that might be a little bit funny to think about. You might be wondering, are there numbers that are not real out there? And yes, there are in fact numbers that are called imaginary numbers, but you don't need to worry about that. That's in much higher math. But it does seem sort of funny to say real numbers. But those are the irrational and rational numbers combined. The next word or definition here is numbers that can be written as the ratio of two integers in which the denominator is not zero. So we'll talk more about that in a second, but those are rational numbers. So they can be written as a ratio, and you'll see that word ratio at the beginning of the word rational there. And really, another way to say that is that they're just numbers that can be written as a fraction. Ratio, it can be written as a fraction with a number on top, a number on bottom. It has to be an integer, which means whole number, positive or negative, and it cannot be zero as the denominator. We don't write fractions with zero as the denominator. Underneath rational numbers, we have a couple definitions here of decimals that are rational numbers. One of them is a decimal whose digits end. So a decimal whose digits end is called a terminating decimal. The word terminating means to end. So if you have something like 0.25, that decimal ends after the 5. There's no more numbers after that, so that's a terminating decimal. That's the decimal form for 1/4. So we know that it can be written as a fraction. So we have the fraction form right there. A decimal whose digits repeat. This one's pretty common sense here. It's a repeating decimal. Make sure you're getting these written in here with me. So an example of that would be something like 0.3333, and the 3 just goes on and on forever like that. I'm going to just use an ellipses to show that. There's another way to show that digits repeat, but for now I'm just going to write that. Both terminating and repeating decimals can be written as fractions. The fraction form of 0.3 repeating is 1/3. And later we'll learn how to do that. We'll learn how to write decimals as fractions. But for now, just know that if a decimal ends, if a decimal repeats, it is a rational number. A number that cannot be expressed as the quotient A over B, or as this ratio, where A and B are integers and B is not equal to 0. So basically the opposite of a rational number. It can't be written as a ratio. That's what we call an irrational number. So irrational numbers cannot be written as a fraction. They go on and on forever as a decimal, and they never repeat. So we'll talk more about what that looks like here in just a minute. The whole numbers and their opposites is our last definition here. And so basically the numbers you count by and the opposites, so that'd be the positive and negative of those. Those are called integers. And we're going to be working with integers a little bit later on, not in this lesson, but soon, learning how to add, subtract, multiply, and divide integers. So let's go ahead and let's move to this chart here. And we're going to classify some numbers here. I'm going to go ahead and write at the top, and I want you to do this with me here. This is real numbers. Let's go ahead and put a "the" in front of that. The real numbers. Alright, so that includes everything in this box and this box. Over here on the left, we're going to start with these first. The real numbers over here that we're talking about are rational numbers. And I've already talked with you a little bit about some examples of some rational numbers. Now I want you to write these over to the side with me here because we're going to draw some other stuff here more towards the middle. So something like 1/2, of course, that can be written as a fraction. Remember, rational numbers can be written as a fraction, and 1/2, of course, can be written as a fraction because it is a fraction. We already talked about 0.25, a terminating decimal that ends, a decimal that repeats. I'm going to go ahead and write 0.3, but this time I'm going to use what's called bar notation. So I'm going to put a bar over it there to show that it goes on and on forever. So that's one way to show bar notation there, or to show that a decimal repeats. And then percents are also rational because they could be written as a fraction. 18%, any percent can be written over 100, so 18% is just 18 over 100. So again, that can be written as a fraction. So those are some examples of rational numbers. We're going to go ahead and draw in the rational numbers a circle here. Make it nice and big because you're going to draw another circle inside of this one here in a minute. In fact, let's go ahead and draw that other circle so we don't accidentally write stuff, so we don't have room for it. So go ahead and draw that second circle. So inside rational numbers, we have a set of numbers that we talked about earlier called integers. Now that's the whole numbers and their opposites, but for this example here, we're just going to write negative numbers because we're going to write the positives in this, and that will include the integers as well. So things like numbers that are already written as a whole number that's negative, like -8 or -3, but also things that equal a whole number that would be negative. So for example, something like -√16. So that negative would stay out front, the square root of 16 is 4, so that would evaluate to -4. But even if we write it like that, we consider that still to be an integer. Or something like -20 over 10. 20 divided by 10 is 2, so we'd still classify that as an integer because in simplest form it reduces down to an integer. Now inside the integers here are what we call whole numbers. So hopefully you got enough room to write that, whole numbers. Now the whole numbers are just the positives of those. So the numbers we count by, but only the positives. It also includes 0. So I'm going to put 0 in here. And things like 12. And also things that would equal a whole number, kind of like we did with the integers. So something like the square root of 25. Square root of 25 is 5, so it's a whole number. And 8 over 2, like 8 divided by 2 equals 4. So even though that doesn't necessarily look like a whole number, when we evaluate it, it does equal a whole number. So in the rational numbers, we have these that are like fractions and decimals that end, and decimals that repeat, and percents. But rational numbers are also integers. That's why they're included in this box. And integers include both the negative and the positive. But whole numbers, you see outside this circle, we have the negative. So whole numbers are just the positives and 0. Integers include the positive, negative. Rational include all of these are rational numbers. So that's why there's a line drawn here, because not included in the rational numbers we have what are called irrational numbers. So write that there. And so we're just going to give some examples of irrational numbers. Like I mentioned earlier, irrational numbers are decimal numbers that go on and on forever after the decimal, and they don't repeat. It's got to be both things that are true. One of the most famous irrational numbers is pi. Now that's a Greek letter, pi, and they use that to represent pi because you can't write the number because it goes on and on forever. So they use this symbol to represent pi. It has to do with circles, and we'll get into that later. We'll actually use pi later in the year. But all you need to know right now is that that decimal number goes on and on forever and doesn't repeat. So I want to show you, I printed out some of the first digits of pi. And if you know anything about pi, you know it's 3.14, and then it goes on from that 15926 and so on. So I printed this out, and there's that 3.14 right there we're so familiar with pi. So it's the whole number 3, and then all this after that is just part of a whole. Okay, this doesn't make this necessarily a big number. It just makes it an irrational number because it goes on and on forever like this. So I printed out on this whole side. These are all numbers after the decimal here for pi. And in fact, on the back side it continues. These are also numbers after the decimal with pi. It just goes on and on like this. And it goes on and on forever. I could have printed out an endless number of pages. I could have printed out 50 or 100 or 1,000 pages like this that just have numbers that go on and on forever. This is what an irrational number looks like. So I want you to picture this. when we think about irrational numbers and talk about them, this is what we're talking about. It cannot be written as a fraction because it doesn't end. There's no way for us to take what comes after the decimal and write that as the numerator and write the denominator with a 1 with some zeros after it. We'll talk about how to do that later on. That's another lesson for another time, but it's coming up soon. But I want you to think of that when we talk about irrational numbers, this idea of a decimal number that just goes on and on like that. Pretty much any operation with pi is going to be irrational as well. So something like pi divided by 4, or pi times 2, or pi plus 3, or pi minus 16, whatever you do with pi is also going to be irrational. The only example I can think of that might still be irrational, we'll put it over here, will be something like pi divided by pi, because anything divided by itself is 1. Technically that should probably go in the whole numbers box because that would be 1. But really almost anything else that has to do with pi is going to be irrational. Some other examples of irrational numbers would be a lot of square roots are irrational, unless, like we had over here, it gives you a whole number, because we know the whole number 5 times 5 gives us 25. But for example, something like the square root of 17. There's nothing we can multiply by itself that would give us 17. So if we try to figure out what number times itself would give us 17, since it's not a whole number, it's going to be an irrational number. If you do the square root of 17 on your calculator, it's going to give you this number that keeps going and doesn't repeat. Your calculator will run out of space, so it will look like it ends, but the calculator just can't show what it really does there. So it really does go on and on forever. And then sometimes you'll just see stuff like this that's written like 1.8926437, whatever, it doesn't really matter. As long as it has this ellipses at the end that shows it really does keep going, then it's going to be an irrational number. If it doesn't have that, then it does end, and you can write it as a fraction, so it would be rational. But if you see that dot, dot, dot. One that will trip students up sometimes is if we have something like, say we have 2.122334444, and put a dot, dot, dot there. It goes on and on forever, and it does not repeat. This is an irrational number. Even though you might be able to, I think you can identify a pattern here, that doesn't mean that it's a rational number. It has to repeat like this, 333, or maybe something like 0.27272727. As long as there's that chunk that repeats, it's still rational. But even though this has a pattern, it does not repeat. So it goes on and on forever, it does not repeat. It would be irrational. Let's do just a little bit of practice here with the time that we have left. And what we're going to do is we're going to classify some different numbers. So I'm going to give you a number. We're going to talk about if it would be rational or irrational. And then we're going to see from there, if it is rational, would it be an integer? If it's an integer, is it also a whole number? So let's go ahead and do a little bit of practice here. Let's start with something simple like 18. So our first decision is always going to be, is it rational or is it irrational? So I'll try to get our chart into view here too. So 18 is a rational number. It doesn't go on and on forever and doesn't repeat. So it's rational. Then we'll ask ourselves, is it an integer? Well, 18 is a whole number. So yes, it's also going to be an integer. And then we're going to ask ourselves, is it a whole number from there? So we're just basically going into the inner circle to see if it continues to qualify. And 18 is a positive whole number, so yes, it's also a whole number. So we're going to say rational integer whole. Let's do another one here, like say the negative square root of 64. All right, well, we need to figure out, is there a number times itself that equals 64, a whole number? So think about that for a minute. Yes, there is. 8 times 8 equals 64. So we could really, if you evaluated this, it would be, it's the same thing as negative 8. So that's really what we're working with here, because we keep that negative sign. So negative 8, is it rational or irrational? It is a rational number. It does not go on and on forever and not repeat. So it is rational. Is it an integer? Yes, it's a positive or negative whole number, so it's an integer. Is it positive? No, so it wouldn't also be a whole number. All right, we're going to do one more because we're running a little low on time here, so I want to make sure that we have enough time to fit this video in the time that we need. So let's do like 3/8. Okay, 3/8. Is it rational or irrational? Well, it does not go on and on forever and not repeat. In fact, it's already written as a fraction, so we know it's got to be rational. Is it an integer? Is it a positive or negative whole number? No, it's not a whole number. It's a partial. It's not a whole, so it's just rational. So we just stop right there. There's no other classification for it, just rational. We'll do some more of these in class, so we'll get to some more of this, and we've got some more practice to do. But that's a good introduction to sets of real numbers and classifying those.